So, good afternoon, everyone. My name is S.Gurumurthy, and I'm from the RWTH Aachen University, and I work as a research associate. My major area of interest is on voltage control for futuristic distribution grids. So for voltage, we plan like 5 sessions. So we have one of them today where I just give a research overview of what we are doing and what other research groups around the world are also doing, just to give an overview. And then we have about 4 sessions on Thursday covering both theoretical and real-time simulation aspects. So today's presentation would have 5 parts. So first I would be talking about the voltage stability challenges in future power grids with the help of some examples. Then we would look into the theory of voltage stability, where it all started, and its extensions to today's power systems. And then we look at since we would learn that impedances are really important to adjust the stability of the system. So we would look at a measurement process of how to extract this grid impedance. Since impedances can be used to change the stability of a system, the control of the impedance of a converter becomes a very crucial part. So we look at some methods on how to shape the impedance. That's why I call it as an impedance shaping approach, to loop shape the impedance such that it's stable with the grid. And finally, from this project RESERVE, we came up with a monitoring technique called as dynamic voltage stability monitoring, and I'll just present this approach of how we are doing it. So the first topic is on the voltage stability challenges in future power grids. So these are the 3 examples that I've taken up. First one is on the medium voltage DC shipboard power systems. During my master thesis, I worked on this area. So here is a typical power system that is there in a naval application in a ship, for example. So you have a medium voltage bus to which the source side converters are feeding power in, and there are some linear loads like a resistive load, or that could be loads which are interfaced through converters again. So the major problem in these in this type of loads which are interfaced through converters is that they behave like a constant power load. That's because their objective is to regulate the voltage at the output, so of the load, immaterial of what the bus voltage is. So from the bus perspective, these converters behave as a constant power load, which means they take constant power no matter what the voltage is. So in order to illustrate that, though, so this is, for example, in a scenario where the bus voltage is stable initially, and then there is a sudden load step change, and this triggers the bus voltage to drop, and then the controller of the source side converters increase the power output in order to match the demand. So here you can see when I use an ideal CPL model, the ideal constant power load model, as shown in black here, you don't see much of an overshoot or undershoot. And when you have, on the other hand, when you have converters operating at 1 kilohertz or higher switching frequencies than the source side converters, you see much higher interactions. There is a back and forth interaction among the converters, and this is due to the fact that the converters can be seen as impedances, and when impedances overlap, you have interactions. So to be fair here, the bandwidth of the 9 kilohertz load is highly limited, because any further increase, it completely destabilizes the system. So just shows you that as the load side converters can be operated at higher switching frequencies, they tend to have higher overlap. The impedance overlap is much higher, and then you have a lot of interactions. So what we learned from the previous example is impedance overlap is a very important phenomenon in order to understand power electronic interactions. So now coming to AC grid, so we have a distribution grid here, the classical one where there are loads behaving in a linear way connected to the grid. But now we are going towards more renewables in the grid, and practically we can see it coming that the households are becoming more towards the DC loads are coming up. So in terms of lighting, and for example, in countries like India, where I'm originally from, all we need, since it's a hot country, you need a lot of air conditioners, and all these air conditioners are now, from induction motors, we are moving towards brushless DC motors. So, it's power electronics and motors come together in something called integrated motor drives. So then, and of course, there is electric vehicles also coming up. So what's going to change first, in my opinion, is the loads first. The loads are going to change to DC very easily. Then the grid, of course, as Professor Didonka was saying, there could be DC grids also. So then this means that there are going to be new converters operating in order to feed these loads. So there could be a controlled rectifier in the household which feeds all your DC loads, and your house could have, let's say, a 120 volt or a 48 volt DC bus. And these converters are going to operate the same way as I explained in the previous slide. So they're going to have a constant power load behavior. And microgrids are also coming up a lot. And so here again we have two scenarios where one, you have a grid connection when the switch S over there is closed, or if you could have an islanded operation where the switch is open, and then you have a voltage control converters coming up, because the converters which have large res behind them, renewable energy, so those ones need to be the frequency makers. They need to form the grid. So these converters operate in grid forming mode, whereas when you have grid connected mode, then all converters can just operate in current control or CC mode, as I mentioned it there. One thing that we need to note here is the interaction among the converters. In the case of grid connection, thanks to the presence of the grid, you could have a low impedance path. So when the converters inject harmonics, if you have a strong grid, then if you draw the Thevenin equivalent, this is more or less like a short or with a very small impedance. So all the harmonics will be absorbed by the grid, and it wouldn't affect the bus voltage. On the other hand, if the medium voltage grid is weak, and rightly so, in futuristic grids it could be the scenario where the medium voltage grid is weak, and then you have a larger impedance, then you have higher interaction among the converters. Similarly, in the case of a weak grid, or a microgrid in islanded mode, which is weak. So so the harmonics injected by every converter does not have a low impedance path or a shunt path where it can sync. Everything would show up in the nodes where inverters are tied up to, and for example, the harmonics injected by this inverter would be measured by this inverter, and it would start to react. So there is no low impedance sync in this case. So in my opinion, it's actually it's a clear point that it's a combination of inverters, if you have more inverters, and the path for a sync. It's both these combinations is which decides how much interaction is going to be there. It's two factors. So let's take an example of a photovoltaic park again. So you have a lot of inverters trying to share the power that is being generated by the photovoltaics. So you could have many strings behind each inverter generating the power, PV strings, and then they are all tied to one point of common coupling, the PCC, and then it's injected into a high voltage grid. So again, if the grid impedance is high, as represented by this Thevenin equivalent, again as Dr. Reis showed in his presentation. So if this impedance is quite high, then you can have interaction among the converters, and you can see suddenly when the grid impedance changed, you can see the interactions happening. So this is what I wanted to explain regarding the resonance. So when you have converters with filters, you always have a resonance. So let's say only inverter A is operating, then you have one resonance peak as shown in blue here. And as more and more inverters are added, the resonance frequencies start to shift to the low frequency regions. And what happens is, when this shift happens, Typically, the control of every inverter is designed with some, let's say, a thumb rule, where I design my inverter's control bandwidth to be roughly 1/10 of the resonance, because this is where the filter is active. So I would design my controller to be active until maybe this region. And now suddenly, because of presence of inverters and combination of grid impedance, if the resonance shifts, then it's within the control bandwidth, so the inverter would start reacting. This is the process of something called as harmonic instability. So therefore, impedance measurement is very important. So in order to better explain, first of all, before going to impedance measurement, how to just put it mathematically, how this interaction is happening. So if you consider two converters, one load converter and a source converter, and you want to study the stability of this point, this interface point P, then you can draw an equivalent circuit diagram which looks like this, which is fairly simple. And then by applying the voltage division rule at this point P, you can write down this equation, and if you just divide this equation by the load impedance, then you see this crucial factor. And equivalently, as a control block diagram, all of this are basically the same thing, it's just drawn in different ways. This is our control engineer would draw, so it looks like a feedback path. So, and this transfer function is the one that decides stability. This concept was brought out by Professor R.D. Middlebrook in the 70s. So it's a concept from 1970s which we're still trying to use and extend. So he says that you always try to design your load subsystem following this criterion, where the magnitude of the source by the load is very less than 1, or make it as small as possible. That's the idea. So it's a very conservative approach. And following this work, there have been many other criterions that have been discovered. And just to summarize, this slide does it. So here is the Nyquist framework, and you have the unit circle here. So according to Middlebrook, you design this ratio of your source by load to be far less than 1, which means let's say I choose this circle or any circle less than the unit circle. So since it should be less than 1. But that's not, so this means that the system will of course be stable, but that doesn't mean if there is a plot, or if there is this curve which doesn't satisfy this category, won't be unstable. So it's only a sufficient condition. So there are other criterions to relax the Middlebrook criterion, because you could have designs where this is greater than 1, but still stability is possible. So there have been various criterions. So some depend on gain margin, so you specify minimum gain margins, or some specify the minimum angle that it needs to, this ZS by ZL needs to have. Or some criterions try to use combination of both. So then you say that the minimum gain margin is this much and the minimum angle is so much, then take the intersection, then you get this forbidden region. So it's a much relaxed criterion. So the plot can lie anywhere, just don't go into this forbidden region. So that's another criterion based on that. Another one which is very interesting for researchers, and we also worked on this criterion, is based on the passivity. And according to passivity, you can be anywhere, but you should be greater than 0. The magnitude should be greater than 0. It should always be on the right side. Then this means that your system is passive, and that means you don't react to disturbances. So that was for DC systems, but now since we want to apply it for inverters, so the previous ones that I presented was applicable for DC-DC converters, but now since we want to extend this for inverters, how do we do it? Since we have sinusoidal quantities, but we want DC quantities. So the approach is to use rotating frame or rotating coordinates. That is, known as the DQ transformation or the path transformation. So what it says is, if you have a rotating framework then of ABC phases, then you have one equivalent phase, and then you can construct two rotating axes which are orthogonal 90 degrees apart, and they rotate with the fundamental. So this approach, so this is the transformation which does that trick, and it's very handy because you can design your controllers to be first order. With a simple PI controller can be designed instead of designing resonant or second order or higher order controllers. So just to give you an example of what DQ transformation does, so if you have a three-phase signal which looks like this, but if you construct your coordinates which rotates with the three-phase signal, then you get just two DC signals. In this case, the Q axis is aligned with the, the D axis is aligned with the A axis. So the way to get there is to use a PLL. So as from the previous presentation, you saw that it is challenging to design a PLL, which is basically a very loyal grid frequency follower, tries to track the grid frequency, matches the phase by introducing changes in the frequencies to match the phase. And in my opinion, PLLs are indeed challenging because any error is propagated into the Q axis, and the control in the quadrature axis will have the dynamics of the PLL. So, however, it's possible to design a PLL if you are considering your control design and the PLL design to be simultaneous. It's like a cascaded system. So you need to understand how the control can affect the PLL and the PLL can affect the controller. So if you can properly design this low pass filters here, then it's possible to achieve a stable design. And it's also possible to use grid frequency feed forward here, which improves the stability. And in the case of unbalanced systems, then we need to use a double decoupled PLL. So which means that you have two sequences, one which rotates with the positive sequence and one PLL which rotates in the opposite direction, and then there are decoupling to get rid of the double frequency components. So then you can use it's just a copy of what you saw before, and just with some decoupling loops to cancel out second double frequency components. So this can be used in the case when the system has unbalances. So just to give an idea of how inverter control is done in the DQ frame, so you have the current measurements and the commands in everything is in DQ, and the grid voltage is measured, and the PLL gives the angle which is used in the conversions for either from the three-phase quantities to DQ or from DQ to the three-phase quantities. So that's just the basics of synchronous reference frame controllers. So what we did so far is we took a three-phase system and converted it into DQ frame. And then you have instead of so a three-phase system got converted into two DC coupled systems. So you have two DC signals for input and output, and there is cross coupling terms. So that's what we have done through the through these transformations. So now instead of a single impedance, we have an impedance transfer function matrix. So in this case, we have a 2x2 matrix. So the ratio that we saw before, from the middle block, that is the ratio of the source impedance by the load impedance. Now it's a matrix. So you see again here you have the source times the load. So again, our source divided by the load in terms of matrices. So Z is the impedance, Y is the admittance, the inverse of impedance. And now, in order to study the stability, we have to plot the eigenvalue plot of this function and see how and apply the same theorems that we saw for DC systems. So that's the extension that you saw for AC systems, and now we have the impedance measurement process. So how to measure this impedance? So we use a concept called as wideband system identification, wherein we say that let's generate some noise signals. So we use a linear feedback shift register logic to generate noise. For example, in this case, there are 15 bits which shift with each clock cycle. The 14th and 15th bit are XOR. By XOR gate we mean at least only one input should be true to this XOR, then the output is true. So that is fed back to the first bit. So this generates a white noise. So this is the algorithm for generating a white noise, which is band limited, and we call it as pseudo-random binary sequence, or PRBS. Literature often uses other names. One of the names is maximum length binary sequence, MLBS. And the idea is to take these perturbations, so these are small signal perturbations, and we add it to the control reference, the current reference. So then what happens is, so you have your fixed current reference, which is something like this. Then on top of that, there is noise that we add with a small, maybe about 5% of the rated current. And these perturbations would cause fluctuations in the currents and voltages. These are recorded, and then we apply the Fourier transform to get the frequency domain values of the voltages and currents. And then by dividing the voltage and current in the frequency domain, you get the impedance. So this is the method. So here's exactly what I explained. You have the noise generation, which is adding the noise to the control commands, and the voltages and currents at the output are measured, and then the post-processing is nothing but calculation of the Fourier transform and calculation of the impedance, which is voltage, the Fourier transform of the voltage divided by the Fourier transform of the current. And you might be wondering, this was just for one impedance, but we saw that for three-phase systems it's an impedance matrix with 4 elements. So how to measure all of them? So the idea is to first add noise just to the D axis and measure voltage D and Q, the perturbations in D and Q, and then you can get these 2 elements of this matrix. Then if you add perturbations to the Q axis and measure the perturbations in the voltages, then you get these 2 elements. So under an assumption that when I measure for the D axis and then for the Q axis, if the impedance remains fixed during this measurement period, then it's okay or it's acceptable to say that I've measured the overall impedance matrix. However, if the impedance is changing fast, then all these elements need to be calculated at once, right? So in this case, we are measuring first for these 2 and then later for these 2. So there is some time gap. They are not measured at the same time. So if the impedance is not changing fast, then this assumption is okay. So here is just an implementation that we did in LabVIEW. So there is an FPGA in the NI National Instruments LabVIEW environment where you can do all this sophisticated calculations, and so the noise is injected into the controller, and the measurements are obtained simultaneously as you inject the noise, and then you have the Fourier transform calculation and impedance calculation. And if you want, you could do some curve fitting to find out do some complex curve fitting to find out the parametric transfer function. Just curve fitting to see what the transfer function is. So just I just picked just an example just to show this concept. A small microgrid. So there are 2 inverters. Both the inverters work in voltage control mode. They regulate this bus voltage here. And there is a very simple passive RLC load network. So you just have resistance, inductance, and capacitances in that network. And inverter 1 is going to inject the noise and measure the impedance. So in the first case, the second inverter is disconnected, and in the second case, the inverter is connected. So just to show the impact of power electronics on the impedance. So in the first case, you see that pretty much the grid is behaving resistive. So that is the passive impedance, whatever its magnitude was, about 20 ohms. You see that. When the power electronics is used, then you see that the resonance effects are showing up. And there is also a change in the phase because of the resonance. So previously I addressed the problem that we have to measure the impedance all at once instead of first measuring the D axis and then in the Q axis. So in order to measure all at once, we need to generate sequences or noise that I can inject both in D and Q axis, but these noise should not interact or be correlated. They should be completely uncorrelated. So a way of doing that is you take your first signal and add the sequence called modulo 2, which is 0101 to the first sequence. It's known as then you obtain what is called as the inverse repeat sequence, IRS, as shown in this blue here. So you see, when the first sequence has energy at a certain frequency, the second sequence has no energy. And when the second sequence has energy, the first sequence has no energy. So this uncorrelated excitations would mean that I can measure the impedances simultaneously. Because in a linear system, the linear system would, if you give an input at one frequency, the linear system would always have an output at the same frequency, just changes in the amplitude and phase. That means I can completely go ahead with this process and measure the impedance. So that was about the grid impedance measurement. We are also doing some to try to build a prototype on that, which I'll cover in the workshop later. So this is now we'll look at how to use the measured impedance and use it in the control process. So I'll just present three approaches based on to change the impedance. So to start with some basics, the LCL filters that the inverters typically use have a resonance frequency, this as I showed before. And this has, as I explained, deleterious effects, can interfere with the dynamics of the control and the PLL when the resonance can shift. So the idea is to damp it. So one of the first ideas that always come is to use passive components. So there are many types of damping that's possible in order to do it passively. This is one example called as a shunt RC damper. So here is your LCL filter with 3 elements, and then this element is added in parallel, which would kill the resonance and provide nice damping. So this is what I mean by damping. The resonance is removed and the phase transition is not as a step, but it's quite smooth. So the disadvantages, however, is very straightforward, is you cannot address changes in the grid impedance. So I mean the resonance frequency. So you think that the resonance is at some frequency and you design damping for those frequencies, but the resonance can shift. Of course, there are possible other options such as trap filter and multi-tune trap filter, which are very complicated to design. So it takes a lot of space, weight, and cost to do that. And again, you always have the problem of what if the resonance shifts to some other frequency than what it is tuned for. So that's why we need to do it actively and emulate it through control. And that's where active damping comes in. So from passive we come to active damping. So here, for example, the capacitor current is measured, and this element here, GAD, the active damping, plays the role of a resistor and provides damping to the resonance frequency. And the goal is to, so this is a very simple strategy, but there are we should come up with more advanced strategies here. wherein wherein the grid impedance knowledge is also used in order to design this transfer function. So there is another approach where the impact of the grid impedance is nullified by first measuring the grid impedance and then using a active series filter here, which I'll explain in the next slide. So what it does is it injects voltages at every frequency to counteract the presence of the grid impedance, and this is known as active grid impedance cancellation technique. So for example, here you see this small power electronic converter which is connected at this node, and it produces it's being controlled to produce a voltage to cancel out the impedance of the grid. So this is another approach. Again, you have to build this converter and have some advanced control in order to do that. So these methods are can be coined as invasive methods, which means you need additional hardware to in order to have this cancellation. But we want to do something in a non-invasive way, where we don't have any additional component, but just use the converter itself and try to tackle the presence of the resonances coming from the grid impedance. So this is one of the work that we recently did. It's an adaptive strategy for designing a virtual output impedance control. So the idea is, of course, to change the inverter impedance by measuring the grid impedance. So the strategy is as follows. The one you see in black here is the typical way inverters are controlled by using the classical cascaded control loops. So you have an outer current control and an inner voltage control. In the case you want to, for a PV inverter, if you want to control the current that you're injecting into the grid, and this current reference would probably come from a maximum power point tracker. So the idea is to use the grid current measurement and use this virtual output impedance control term, and this modifies the capacitor voltage command. So the capacitor voltage command which comes from the outer control. So if I do the mathematical formulation and try to find the transfer function from Ig to Vg, then you get this, the output admittance of the inverter. And here you can see the presence of the VOI term that I introduced. So if the VOI term is not there, then it's just like this term is 0 here. When the VOI term exists, then this term, you can see that it modifies the outer control transfer function. So basically it's controlling the dynamics. In literature, virtual output impedance control, or this VOI control, is used for power sharing. In this case, this is not for power sharing. This is for controlling the dynamics. If I have a transition, this block would kick in and give the inputs here in order to regulate the way the capacitor voltage can change. That's the idea here. It's to control the dynamics. And the process for designing this is as follows. So as I said, the grid impedance measurement is very important because we want to design our VOI control based on the grid impedance. So we first do the measurement process and the measured grid impedance. So the measured grid impedance and the filter inductance of the LCL filter, the sum of them is just called as this term ZT, which can be augmented into the control block diagram of the inverter, which I just showed in the last figure. So this part can be, or this part can be removed, and you can replace it with the help of the total impedance. Then now you can see that the design objective is this, to design this, and this entire control transfer function control of the inverter is like the plant that we want to control, and the objective is to synthesize this ZVOI such that the output current has a certain characteristic. So for example, this weighting function allows me to design the bandwidth of this current variable Ig. So if I know that the resonances exist at certain frequencies, then I can use a weighting function which is band pass in order to achieve a loop shape of band stop. The weighting functions are like punishments, so you get the opposite effect. So if you want to have a band stop characteristic, your weighting function should be band pass. So this, I would probably design it to be a band pass, and then I can achieve a design of band stop from this in order to loop shape it to be a band stop. So in my case, I have used the approach of linear loop shaping. So it's just one of the methods called H infinity control. It's a norm-based method to minimize or suppress the peaks. So resonances are peaks, and we want to suppress those peaks. That's the idea. That could be many other norms or many other ways or optimization techniques to calculate. So it's completely open to come up with new ways to calculate this virtual output impedance control. So this is the idea that we recently wrote. And finally, I want to present the idea of the monitoring scheme or the technique that we came up in RESERVE. It's called as the dynamic voltage stability monitoring. So here is our inverter, and there are many other inverters in the grid. And you have the secondary substation automation unit, or the SSAU, which is just the distribution substation. So the idea is to for this inverter is to modify its impedance so that it doesn't contribute to resonances. So we know that we first have to measure the impedance. So the substation acts like a coordinator, asks the inverter to inject noise, and so it does, and gets the perturbs the currents and voltages in the small signal sense, then does the impedance calculation as seen by the inverter, and does curve fitting to get the transfer function of the impedance, and it sends this transfer function, just the coefficients on all these coefficients A2, A1 and so on, back to the substation. So it sends not only this but also the inverter's self impedance or its own output impedance to the substation, because as we know, in order to evaluate stability, we need the grid impedance and the inverter's own impedance, the ratio of the source and the load. So the inverter measures the grid impedance because it's unknown and sends it to the substation, and the inverter knows its own impedance mathematically because the inverter's impedance depends on its operating point, its control parameters, and its physical filter parameters. So it can be mathematically formulated, as I showed in one of the previous slides. Then there could be impedance-based stability monitoring. So we'll do an exercise on this, how to do this plot on Thursday. So I'll explain you how to draw the characteristic loci when you have the impedance information. And once the stability margins are analyzed, then you can use that information to apply the virtual output impedance control that I just explained in the previous slide. And the virtual output impedance control is a linear controller, just some coefficients which sends it, which the substation sends it back to the inverter, and the inverter then changes its impedance. And when we say it changes its impedance, it's just implementing those damping schemes at higher frequencies. So it's a higher frequency behavior change. So this process can be made in an adaptive way, just to as an automation to repeat this process. So you measure the grid impedance, calculate the controller, and then back again. So you can do this many times or keep on doing this monitoring. And here's where we also try to come up with some grid codes, where we can say once we did some kind of stability monitoring, so we can try to define some margins such that we can take action or we don't take action. By action I mean design of change the impedance of the inverter. So this is the monitoring idea. So to conclude, The impedance-based method is a very promising tool for analyzing small signal stability. You can design interconnection of many power electronic converters, because that's where we are heading to. We want to have passive interconnections, because passive means you reject noise and try to not react to noise or harmonics. So passivity is always good. And finally, we can use grid impedance for both monitoring and control. And as I already explained, we can try to come up with some advanced impedance shaping control for damping the resonances, which are the major causes of harmonic instability. So that's it from my side. On Thursday, we'll look into more details and try to do some examples. So that's it. Thank you.